Alright, so this video is going to mark the last stretch of videos we do, well, that I do, for this logic course. Not really a course, more of a supplement to a course. But today, we're going to be moving to non-classical logic. Now, a lot of what we've done will remain the same. We'll still use capital letters for parentheses. We'll still use lowercase letters for our parameters. Our connectives will stay the same. Disjunction, conjunction, negation, conditional, and equivalence. Only difference is with negation. Now, instead of using a squiggly for our tilde, it'll look like that. It doesn't really matter if you forget and use the previous one. I'm going to try my best to use this new one, but it's understood that they're both negation. So that's a difference. We'll introduce Greek letters later because we're going to do some proofs and they will help us with some shorthand. But the big difference are these trees. As you can see, we're doing a tree method for validity. So now we need to know what a tree is, how we use them, and what they look like, right? So a tree is a ton of dots connected by lines. These dots are called nodes and the lines are called edges. So our trees are going to look something like this. That's just an example of one tree. As you can see, there's the dots, the nodes, and the lines, the edges that connect these dots. So how are we going to use them? Well, here's what we are going to do. We're going to take connected parameters such as P and Q, P or Q, not P and Q, not P or Q. Basically, we're going to cover all of our bases and see how these work in a tree format. So, because that's the thing, our dots are going to be replaced by parameters. They might just be lone letters like P, or they might be not P if and only if Q. So let's see what we would actually do, how we can go from having a parameter like that and expanding it down the tree. So here's what we would do. If we have P or Q, for example. So if we have P or Q, how is this going to be written? Well, with our disjunction, we are going to separate this into two different branches. We're going to say P or Q. So we have two different, and we can imagine these kind of as paths, like crossroads, right? You're somewhere and you can either go left or right. Right here we have P or Q, so we can either go to P or we can go to Q. So the tree splits, P or Q. Now what about P and Q? Oh, and by the way, if you just have a single letter, then that's it. There's nowhere else to go. So it would just stop right there. Now what if we have P and Q? So if we have P and Q, right? Well, there's no disjunction anymore. P and Q are kind of stuck together. So what we do is we only have a single path that contains both P and Q. So we just write them on top of each other. I'm going to erase this tree because I think it's going to get in the way. Okay, so we have that. Now what about their negations? What about not P or Q? Well, remember, we know what not P or Q is by De Morgan's law, right? With De Morgan's law, not P or Q becomes not P and not Q. And we know how to write conjunctions, so that's exactly what we'll write. We'll draw one branch down and we'll say not P and not Q, right? And then we'll use that same kind of logic when we do not P and Q. Right, by De Morgan's, we know that that's equivalent to not P or not Q, so we'll have one branch going down to not P, and another branch going down to not Q. There you go. We're almost halfway there. Now what about our conditionals, right? If we have P then Q, so if we have P then Q, what do we know about this from our rules of inference? We know that P then Q is equivalent to not P or Q, right? So we have not P, we have Q, and then we have our disjunction or. So we just write two different branches, not P or Q. So you see how this is going? It's really not that difficult. You're just going to, if you've made it this far and you know all these implications, all these inferences we can make, this really shouldn't be too difficult. Okay, so we have P then Q. What about not P then Q? So if we say not P then Q, Remember, P then Q is not P or Q. So if we negate that whole thing and we De Morgan's it, we'll get P and not Q. So we have P and not Q. There you go. 3 more. We're going to talk about our conditional now, right? What if we have P if and only if Q? P if and only if Q. Now remember, P if and only if Q can be interpreted as P and Q, or not P and not Q. So we have P and Q, or not P and not Q. Likewise, if we have not P if and only if Q, well, that's the case when one parameter is of one parity, so one parameter is true and the other is false. So this would be P and not Q, or not P and Q. Now you might be wondering, Johnny, you have 8 things right now and you said there were 9, but this looks like it covers everything. Well, it doesn't, because we have double negation. So if I have not P, we could just double negate that to P normally. So these are our expansions, our rules for this kind of tree format, right? So that's all good and well, but how is this actually going to help us? How are we going to use these trees to determine validity? Let's do it. The first difference we're going to discuss is how we write out a list of premises and then our conclusion. So here's how we would do that. So if we're using, remember, capital letters like normal for premises. Let's say we have premises A1, A2, AN, right? So this just means we have some n amount of premises. And then we'll say, therefore, that's how we draw it. It'll look like that. B. So A is the list of premises, and B is our assertion. It's our conclusion. We're saying if we have these premises, then we can argue B. So that's just going to be the notation for it. Now, how do we tell if this is a valid argument? Well, here's what we're going to do. Let's do a little example here, and I have one already planned out. Let's say I wanted to argue if P then Q, and if Q then R, so those are my premises, I want to argue P then R. Now, you should know this is true from a hypothetical syllogism, I believe that's what it is. We know that this is a valid argument. So how do we actually argue this? Remember when we did indirect truth tables? We had some set of premises and a conclusion, right? And what we did is we assumed the premises were true and the conclusion was false. That's an invalid argument. So we assumed it was invalid from the beginning. And if by doing so, that led to contradictions, then we would say, okay, assuming it's invalid, it's contradicting itself, therefore our argument must actually be valid. We are going to be doing the exact same thing here. What we're going to do is we're going to take our set of premises, right? Assume them to be true, and then assume the negation of our conclusion. We're going to draw out these trees, and if we hit a contradiction on every single branch, so the entire tree closes, if we hit a contradiction on every single branch, then we know that our argument was actually valid, right? We hit contradictions by assuming the negation, so therefore we undo our negation and say the original argument is valid. However, if a single branch is left open, just like with our indirect truth table, if we assumed it was invalid and we didn't get a contradiction, then okay, the argument's invalid. It'll be the same here. If we don't get a contradiction on a branch and it remains open, then the argument is invalid. So let's see what I mean by these contradictions and closing branches. So let's write out our tree. What we're going to do to write out our tree is start by just writing our premises and negated conclusion on top of each other. So I will write P then Q, Q then R, and I'm going to write not P then R. And now here's what I'm going to do. I'm going to start using these expansions that we just kind of went over, our new kind of rules of inference. And I'm going to expand upon these premises and negation and negated conclusion until I can no longer do that. So let's start with P then Q, right? I said that P then Q would be not P or Q, right? That just comes from our... Oh, actually, you know what? Here's what I'm going to do. I think it's best to start where you can when you have a conjunction. So I'm going to start with that negated conclusion because that's going to be P and not R. So that's what I'm going to do first. So I have P and not R, right? And maybe that's the top of our tree, so I don't need to draw a branch. This is the top of our tree, P and not R. And one thing I like to do is just check off where I've already expanded so that way I don't try to do it again later. So I've already done this, can't do it again anymore. That's the big rule. It's like once you've done it once, I can't just repeat it again later on the tree. That's going to mess stuff up. So we got rid of our negated conclusion. Now let's look at our premises, right? That's all we can do. So P then Q means not P or Q. So let's write that out. So we have not P or Q. And right now, we've just hit a contradiction. We get a contradiction when on one of these paths of the tree, we have a parameter and a negation of that parameter. So in this case, we have not P and P following along the same path, right? And a path here, let me just highlight this in like yellow. This path could be like right here, like this is our path. And on it, we have not P and P, so we close the branch off, we draw a little X underneath it, and say, this is a contradiction, this branch is closed, we are no longer going to operate on it, because what's the point? It's a contradiction, it's a contradictory branch. So now we just follow our path of Q, and we mark that we've already expanded upon that, and we're done with that. All we have left is Q then R. So again, we know that this argument is valid, and we're assuming it's invalid, so we're going to hope that this expansion will just get a ton of contradictions for us. So Q then R turns into not Q or R, right? So let's write that out. Not Q or R. Now, as you can see, we have not Q and Q on the same branch, so that's going to close. And then we have R and not R on the same branch, so that's going to close. And there's nothing left for us to do. We can't expand upon anything. Our branch is completely closed off, meaning there was a contradiction every time we assumed that our conclusion was false. And so if by assuming that our conclusion is false, we only hit contradictions, then it must be the case that our conclusion was true and our argument was actually valid from the start. Meaning, if we have the premises, P then Q, Q then R, we can conclude P then R. And we knew that already, right? So let's do an example of a tree that will, I don't know. Let's do a tree. This could be difficult. Okay, I have an example of a tree that will not close, okay? So let's do that. So my premises will be right here. We have, so we have P, and yeah, these trees can get complicated. That's why I'm being careful in choosing ones that will fit on screen. So let's say our premises are P and not R or S. And then we have not Q then S. So P and not R or S is our premise. Q then S is the conclusion, and we're negating it because we're going to do our tree method. We're going to see if this is, here, let's write it out. We're going to see if this is a valid argument. Let's write it out. P and not R or S. And we want to conclude Q then S. There you go. I'll just write that in parentheses. So let's start this off. What can we begin with? This is... I don't like this. I have no idea why I chose it. Oh, actually, let me redo this tree real quick. I have notes written by me, and so that's why I copied this down wrong. So not Q then S is actually another premise, and then R is our conclusion, so we negated that. So our premises are P and not R or S. Then we have not Q, no, that's a G, not Q then S. and we want to conclude R, or we're going to see if we can. So let's start with our tree. So the first thing we could do is our, right at the top, we have a conjunction, so let's deal with that. So the top of our tree will be P and not R or S. So there we go. We've used that, we're done with it. Now, what's the next thing we can do? Well, I'm going to split our not R or S into two different paths. Let's make this not R and S. So there we go, we're done with that. The only thing left that we can expand upon is the Q then S. Well, the not Q then S. So what is not Q then S? Remember, that can become not Q or S, and then when we negate that, it becomes Q and not S. So we have Q, not S, and what we have to do is put this on both of our open branches. We have to cover this on every open branch. So that's a rule when you're doing this, is when you expand upon something, you have to do it to every open branch. So on the right branch, we could see we have a not S and an S, contradiction. However, the left branch is open, right? And there's nothing left to expand upon. So we assumed our argument was invalid. And although it led to one contradiction in one case, in another case, there was no contradiction, meaning that it's possible with this argument for the premises to be true and the conclusion to be false, which is an invalid argument. So we're going to say that our argument up here is invalid. So when we're doing these trees for validity, we want the branches to close. That's how we know that it's a valid argument. I want to do one more example of a valid tree, just because, why not? If you want to tap out now, you understand that you can, but I'm going to do one more tree, and it's going to be valid. So our argument will be P then Q, P then Q, R then Q, and what we want to argue is if P or R, then Q, right? This should look true. We're saying P then Q is true and R then Q is true. Therefore, if we have P or R, we know Q will be true. In fact, if we have P and R, it'll be true. So this is a valid argument. So we should see that all of our branches are going to close. So let's start writing out our tree. So let's write out our premises, P then Q, R then Q, and then negate. Have to put another bracket around these. Let's draw parentheses. P or R, then Q. There you go. And so now let's just start expanding, right? So what I want to do is start with our negated conclusion, because this is of the form, like not P then Q. So what we're going to have is, that's supposed to be an R, right? Yeah, that's supposed to be P or R and not Q, which is what we can gain from this. So this will be P or R and not Q. That came from here. We're done with that. Right, next thing I want to do is just work on our disjunction, P or R, right? So let's split this tree into P, or R. There we go. We're done with that. Now, nothing left to do except for expand upon our two premises. So let's just start with the first one. So the first one will be not P or Q. So we'll have not P or Q. It's a contradiction from not P and P. So let's just cross that out. Now we have to expand up. Oh, and we have to do that to both of our branches. Don't forget that, like I almost did. So not P or Q. As you can see, these trees start to get pretty cluttered if you don't spread them out nice enough. Now we have Q and not Q here. So this branch closed. So we only have two open branches left. And our premise R then Q. So that will expand to not R or Q. So let's mark this off. This will be not R. This will be Q. And we have to do that here as well. So not R or Q. Sorry, it looks like 7R. So it looks like 7R as well. Not R or Q. And let's see. Do we have contradictions? Yes. So right here we have Q. If we follow the branch up, we reach a not Q again. So this closes. Do we have? I feel like we should have had a contradiction right here, and I'm not seeing it for some reason. I see the contradiction. This branch was supposed to close before. So you could see we have a Q here and a not Q up here, so that should have closed. This one will close right now because we have Q, and again, this not Q is getting circled a lot, so that's going to close. And then we have not R, R right here, so that will also close. So we have, when we assumed the argument was invalid, we reached contradictions everywhere in all possible cases. Therefore, it must be the case that our argument actually is valid. So there you go. That is the beginning of our non-classical logic journey. We will not stop doing trees. Trees will be everything, except for maybe one little thing at the end. But yeah, I think this is actually a pretty cool thing to do. It can get messy drawing these trees. But I think the rules of inference are very easy to remember, especially if, I mean, you should know them by now if you've gotten this far. I think they're easy to remember, and it's just kind of fun to do. As you can see, it's easy to make mistakes. Like, I almost got lost on this branch right here. I should have closed it a step earlier, and instead I just kept going. So you need to make sure you go back and check your mistakes. But yeah, it's actually pretty cool. It's what we're going to continue to deal with. But yeah, if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.